Hello, this is Professor Stephen Neshiba, and I'm here to help you out with the computational exercise having to do with probability densities. Here's the handout on that, probability densities, and there's a number of objectives that we have, some vocabulary, and equations. And part of your pre-lab, of course, on this will be to write down some of those equations and carefully read that introductory material. And also, you'll want to look up the value of the gas constant and the molar mass of a few gas molecules in the SI unit system. So I can just tell you that the molar mass, or the gas constant, that's 8.314 joules per mole Kelvin. The molar mass is going to be a bit tricky because you're used to grams per mole, but if you're going to be talking in SI units, that has to be kilograms per mole. So you would divide by 1,000 compared to what you might expect. So that's having done that. Now you're perfectly welcome and encouraged to launch into the in-class activities as part of at home before you come. So, and I'm here to kind of help you out a little bit on that. So, first one is display the Boltzmann probability density function. That's FB. That's Boltzmann density function is a function of the speed in the x direction, velocity in the x direction, and the temperature as a two-dimensional surface. And we want to make the velocity components range from minus 2,000 to 2,000, and the temperatures from 100 to 1,000. So I've already taken the liberty to download all four of these, the four templates that are on the website. And so here's kind of what you'll do. These are sort of standard resources that we need. This third part allows us to do the surface plots. There's R, that looks good, 1 mole. The mass, I've set at 0.028, that corresponds to nitrogen gas, N2. Our velocity or components are going from minus 1,000 to 1,000. We don't want that. We want it to be in the range 2,000, and then the temperature we want it to go from 100 to 1,000, as I recall. Yeah. And so let's see what else we got. Now, this d is just an intermediate quantity. It's the thing that multiplies the speed squared in the exponent. So that's just d, and that I just put it out there as a easier way to read it. And this is the normalization constant, and so on. So, and the graphing it all looks okay so far. So I'm going to go ahead and execute that, and hopefully we'll get a graph out of it. So there's the graph, and well, that looks pretty good. You can click and rotate it, of course, and you'll want to study that a bit. Now, there's one more thing that I asked you to do on this, which is put appropriate labels. I think we've done that, but it's cosmetically nice to multiply the z-axis by 1,000, and you can kind of see why that's the case. It's got these small numbers here. So why don't you see whether you can make that change right now? Okay, well, there's various places you could make that change. We could divide this by 1,000 right now, or we could on the fly divide that by, multiply by 1,000. I can do it right here, times, and I could say 1,000, but 1e3 is another way of saying that. So let's see how that works, and hopefully that will come up. Okay, well, there we go. It's now multiplied the Boltzmann distribution density by 1,000. All right, that's good. And now what are we going to do on part 2? Display the Maxwell probability distribution. So now we're dealing with FM. Now we want to go from 0 to 2,000 meters per second, because the speed is positive number, temperature in the same range. And let's see if I can figure out what to do here. So that's the template that you could have downloaded, and let's see, this all looks pretty good. Same thing, molar masses corresponding to nitrogen. Let's see, we wanted the speed to go up to 2,000, and again we wanted the temperature to go from 100 to 1,000, and well, we'll just see how this works. Get our graph up here. Yeah, okay, well, that looks good. The speed is going now from 0 to 2,000 and so forth. We still have kind of a, this could be be nice if this were multiplied by 1,000. So I'll let you figure out how to do that. Let's see, what's the next thing that we want to do? Calculate the moments of the x direction velocity component. We're supposed to calculate the first 4 moments, and starting with the first moment, which is just the speed times the distribution function, or the density function. So let's see how that works. I'm going to go to PD3 template, and alright, looks all pretty similar up here at the top. We've got the Boltzmann function there again, just as before. Oh, now this is already done from minus 2,000 to 2,000. And well, for this one, we're not doing a surface plot, so we're just going to do a simple plots. And let's see what happened. Oh, the integrand in that, and this is the integrand in this equation right here, equation 9. Or rather, sorry, the integrand in equation 8 here. And let's see how that's been done. Yep, there's the Boltzmann function times the speed in the x direction. There it's being integrated. That's the trap z integration function. And well, I think we're good to go on this. Let's see what happens if I run it. Well, there's the integrand from minus 2,000 to plus 2,000, and how did our the integral came out according to the trapezoidal rule? Looks like it came out to this very small number, which you'll have to figure out how to interpret.